Hello, hello everyone. So we'll start today's live session within a minute. We'll wait for everyone to join and then we'll start today's live session. So please just raise your hand for the answering the questions, or maybe if you want to ask the doubts. And let me share my screen to with you, and just please confirm that if my screen is visible or not. Okay. So yeah, am I? My screen is visible. Okay. Okay, great. So let's start today's live session on modern construction materials. Hello everyone, myself Umesh Vole. I'm PMR FTA for the course Modern Construction Material, guided by Professor Ravindra Gattu from IIT Madras. So we are in the week 11 of live sessions on modern construction material, and we have covered a lot of different topics on concrete, its durability, its properties, different type of materials like wood, timber, aluminum, and many more metals which are used in the construction industry. And now today we are going to cover a little bit about the concrete, its durable properties, and different attacks on concrete like sulfate attack, carbonation induced corrosion, and then we'll see also chloride induced corrosion, chloride ingress in the concrete, how to mitigate that, how to reduce the ingress of chlorides, and also reduce the corrosion rate if there is also corrosion is happening by different productive methods we will see. And also we will see some of the special concrete which use in the construction industry, for example self-compacting concrete or fiber reinforced concrete or ultra high performance concrete. Also we will see some of the questions regarding that, how we prepare it, what are the different characteristics of ultra high performance concrete, and where its applications is nowadays are there. We will see that, and also we will see some of the characteristics of fiber reinforced concrete, why we use fibers in a concrete, and what properties is enhanced by using the fibers, and what are the different fibers. Also we were going to see, actually we have covered a lot of content in the previous lectures regarding fibers. We will see the application now. Okay. And some of related to the specialized concrete like lightweight aggregate also we will see today. Okay, so let me start with the question number 1. Is on your screen. It's like that: what is a sulfate attack in concrete? Primarily involves a reaction between sulfate ions and what? So in sulfate attack, what is that reaction which causes the deterioration to the concrete? What is that reaction between which two components of the concrete? Is it from silica in aggregate? Is it from hydrated calcium aluminate phases like eternite in the cement paste? Or is it with the calcium carbonate in the cement paste or iron oxide in the cement? You can type answers, or you can unmute yourself and just mention the option number. Anyone with the answer? It's easy. Sulfur attack. Okay, let's see the answer. Because it's easy, we will not take much time for this, and we have today a lot of questions, so we are trying to cover all the topics related to concrete durability. So the answer for this question is B, where is the reaction between hydrated calcium aluminate phases like eternite in the cement paste, and which will lead to expansion stresses and leads to cracking into the concrete, which is called as a sulfate attack. Okay, let's move forward to the next question. So the question is on which one of the following is the common source of sulfate ions that can attack concrete structures. Now we have seen that what is sulfate attack, because if there is sulfates, if sulfates are going inside the concrete, that will react with the eternite phases and forms expansive products, which will lead to cracking. Now from where they can come: carbon dioxide in the atmosphere, chloride salts used in de-icing, groundwater and some soil, and option number D is organic acids from de-icing vegetation. These are the different sources, which are the probable sources from which there is a possibility of coming of sulfate ions, which can lead to sulfate attack into the concrete structures. Yeah. Okay. Will not take much time for this, so we'll give you 1 minute, and then we'll move forward for the next question. Okay, let's see the answer. So answer C is correct, like from the groundwater and some soil which already contains sulfates in it, which will lead to ingress of sulfate into the concrete matrix, and that will lead to the reaction with the ethylene gas, and which will lead to the formation of expansion products and will lead to cracking. Okay, the next question is on which one of the following measures can help mitigate the risk of sulfate attack in concrete structures. Now, if there is a possibility of sulfate attack into the concrete structure, how we can prevent it? So, the option is increase the water to cement ratio to improve workability. Use a concrete mix with a low permeability is the second option. Covering the concrete for short duration is the third option, and the fourth option is using aggregates with the high sulfate content. Think on it. We'll give you 1 minute to think on this, and then we'll move forward to the next question. Okay, anyone with the answer? Okay, answer. Okay, answer B is coming. Okay, anyone with another answer? Okay. Okay, let's see the answer. Answer B is correct. Using the concrete mix with a low permeability can reduce the risk of sulfate attack, because there is no possibility of ingress of water with rich in the sulfate ions, which you can enter inside the concrete and react with the additional product to form expansive products. Hence, using a lower water to cement ratio and lower permeability concrete can be one of the solution to mitigate the sulfate attack into the structures. Okay, let's move forward to the next question. So next question is on sulfate attack is generally more severe in dry concrete structures that are submerged continuously submerged in the sulfate-rich solution, well-cured concrete with low permeability, concrete made with sulfate-resistant cement and high water-to-cement ratio. So where will be this is more severe? I think it's easy. Okay, option C. People are saying. Anyone with another answer? Okay, some of them say. Okay. Some of this B is also can be correct. Okay, let's see the answer. Yeah, option B is correct, not C. Concrete structures that are continuously submerged in sulfate-rich solution as having high probability of increase of sulfate ions in the concrete lead to sulfate attack. Correct. Next question is on carbonation in the concrete. What is the carbonation of concrete? Is it and what are these properties we will see now. So the first question is on carbonation of concrete is a chemical process where atmospheric carbon dioxide reacts with what? With what element or with what hydration products into the concrete structure? carbon carbon dioxide reacts, which is reacts with the silica in aggregates, hydrated calcium silicate CSH, calcium hydroxide in the cement paste, unhydrated cement particles. It's easy. Then we will see what is carbonation in general, and then some of the problems related with it. Okay, let me tell you what is the carbonation. First of all, carbonation is the reaction between the CO2, which is present in the atmosphere, and concrete pore solution where there is some ions present. And when CO2 enters into the concrete structure, initially it dissolves in the pore solution of concrete, forming a carbonic acid, and then for the reaction with the ions and hydrogen products into the pore solution, it forms calcium carbonate. That reaction is called as formation of calcium carbonate, which is nothing but the carbonation of concrete. So just now we have seen what is the reaction. So which that is constituted of pore solution, or in general in a cement, what is that oxide responsible for carbonation reaction. Okay, some answers are coming as C. Okay, some people are saying B also. Let's see the answer. Answer C is more appropriate. Yeah, so the primary reason where first of all the reaction of CO2 happens with calcium hydroxide, CaOH twice, and that leads to the formation of calcium carbonate and called as carbonation of concrete. However, in some of the newly developed concrete where there is a very less availability of calcium hydroxide present, in that case the reaction of CO2 can happen with even hydrated calcium silicate or CSH structures of the concrete, which can lead to decalcification of CSH structures and loses integrity, and can lead to coarsening of pore structures and also reduction in the durability of that concrete. So that is the secondary phenomena usually happens when there is a high replacement of mineral oil mixture is added, which leads to reduction in the calcium hydroxide content in the pore solution. Because of that, CO2 directly attacks CSH structures. Hence, for now this question in a general, C option is correct. We'll go with the C. Okay, if you have any questions, you can ask now, or we'll see the next question. Okay, I think it's clear. Let's see the next question on carbonation. The primary effect of carbonation on pore solution within the concrete is. So now we have just seen the carbonation. What is the carbonation and what is the reaction with the carbon, which leads to formation of calcium carbonate into the concrete. So now what is it leading to in a pore solution of concrete? Option A is significant increase in the pH alkalinity. B, significant decrease in the pH alkalinity. C, increase in chloride ion concentration. D, decrease in sulfate ion concentration. Yeah, it's very easy question, will not take much time. Let's say 30 seconds for this question and we'll move forward. Okay, let's see the answer. So answer B is correct. Yeah, many people have answered. Okay, significant decrease in the pH of alkalinity is the consequences of carbonation that leads to reduction in the pH, and the reduced pH can lead to Decalcification of passive flame, sorry, pH, reducing in pH can initiate the corrosion of a steel if there is a steel reinforcement is there, and that's why carbonation is also important to study. Okay, so the next question is on which one of the following factor can accelerate the rate of carbonation in concrete structures. Uh, let's say for example the areas which is away from sea. Let's say for example in this case we can consider Pune is one of the city which is away from sea. So what is that condition which can accelerate the carbonation, which is as high? Option A is the high humidity levels, B dense impermeable concrete, C low level of atmospheric carbon dioxide, and D porous concrete with a low cement content. Or you just take example of any city which is just not nearer to the sea can be considered for this question. So what is that parameters, what is that factor which influences the carbonation rate is the logic behind this question. We'll see. Okay, some of people are saying D is the answer. Okay, anyone with another answers? Okay, D. High relative humidity, okay, high humidity levels. Okay, okay, let's see the answer, or maybe we'll see to eliminate from the options and then we'll see what are the answers from it. Okay, so dense and impermeable concrete obviously is not answer because it will reduce the ingress of CO2 into the concrete structures, and that eventually will reduce the carbonation of the concrete. Okay, low level of atmospheric carbon dioxide, obviously the lower the carbon dioxide levels is lower will be the carbonation, so hence we want to accelerate the carbonation, so we want to to happen that we will require a higher level of carbon dioxide, so that's also option is not correct. So now option A and D, from that some people are saying A, some people are saying D. Let's see the answer. So answer D is correct. Obviously the porous concrete with the low cement content will lead to higher carbonation because the porous concrete will allow CO2 easily to enter inside the concrete matrix, and with the low cement content then the carbonation will be faster because there is the product which is carbonatable content will be less. For example, calcium hydroxide and other CSS structures, they will be less in quantity and it will be easy to carbonate them. Higher relative humidity will not be the answer because as it's observed that the carbonation rate follows trend like this, where higher carbonation rate is observed around 70 to 80 RH, and after that it is lower, and before that is also lower. So what could be the reason is that when there is a lower RH, then there will be the very less, when there is a lower RH, so this is carbonation rate, let's say for example K, and this is RH. So now we are seeing that the RH and carbonation rate are related. In the lower RH level, the carbonate rate of carbonation is lower, and also at the higher RH, for example nearer to the 100, the rate of carbonation is again lower. So what could be the reason? So at the lower RH, there is a possibility of the pores inside the concrete structures are not filled with enough pore solution, and hence when CO2 is also when there is a ingress of CO2, because now pores are empty and CO2 can easily ingress inside, but however there is a very less amount of post solution is available, then the reaction will be limited because of formation of carbonic acid will be limited, and that to formation of calcium carbonate will be also limited in the lower RH levels. What will happen at the very high RH level? For example, 95% of RH, what will be this condition at the pore solution? Pore solution will be very high. Many pores may be have blocked with the water, and it will be difficult for CO2 to enter because of presence of high moisture into the pore structure. That's why the carbonation rate is also lower at very high RH levels. So hence at the 70 to 80, the optimum level of RH where the carbonation rate was observed to be highest, because at that level some of the pores are filled with full moisture, but or partially filled with the water, hence it's allow ingress of CO2 also, and also dissolution of CO2. Hence that is the reason for having the higher carbonation rate around 70 to 80 RH levels. And we have seen that in the porous, more the porous concrete, more will be the carbonation, lower the cement content, more will be the carbonation. So the how the lower cement content is generally happen, like when this is nowadays this is happening a lot, because people are going for uses of indirect admixtures like supplementary cementitious material, fly ash, GGBS, silica fume, metacolin. If they use in a very high amount, the cement content in that is will be very low. That's why uh, the reaction of carbonation is also higher in that case. Okay, so this one is about the carbonation. We'll see the next question is on the loss of alkalinity due to carbonation in concrete depassive the steel reinforcement by. Okay, so how the depassivation of steel happens due to the carbonation, what that leads to? Option A, forming a protective layer of calcium carbonate on steel surface, dissolving the passive oxide layer with the protect the steel from corrosion, increase the electrical conductivity of concrete, decreasing the availability of oxygen at the steel surface. So what is the answer from this? Like what that leads to concrete depassive the steel of reinforcement by action of. You can just type your answer in the chat box, or just unmute yourself if you have answer with you. Anyone with the answer? It's an easy question, like how the carbonation leads to corrosion by to the steel. What will happen to the steel when there is a carbonation? In general, this is the question. Okay, let's see the answer. Answer B is correct. Dissolving the passive oxide layer that protects the steel from corrosion. So what is the passive layer? Just we have seen in the previous live session where that the higher pH of concrete leads to formation of passive oxide layer onto the steel surface. So what is that? As we know that when we pour the water into the concrete, and cement will start hydrating, and because of that the supersaturation happens, and the pH of concrete increases up to the 13 level, and that pH is favorable for steel in a concrete because it forms oxide layer, which is called as passivation of the concrete, which prevents the corrosion for some time, because now there is some layer formed onto the steel surface that will protect the ingress of the chloride ions or many other elements which can corrode the steel beneath it. Okay, the carbonation is one of the also reason to dissolve that oxide fell by due to the lower pH. The lower pH is around 9 can leads to depassivation of the steel. The passive oxide layer will destroy because of the lower pH and can lead to corrosion due to carbonation and dissolution. Yeah, due to carbonation. Okay, so the next question, for example, in Pune environments or the any city which is inland and not exactly near to the sea, which one of the following measures can help prevent the minimize the carbonation induced corrosion? We want to reduce the carbonation induced corrosion because we want a high service life of any structure we have. How can we do that? Because we can't reduce the CO2 into the atmosphere as we required. That's very global level problem. So the options are using concrete with the high water to cement ratio for better workability, ensuring adequate concrete cover to the reinforcement. Using the third option is that using highly permeable concrete to allow the faster drying, avoiding the use of supplementary cementitious material. Please make sure you are scientifically selecting the answers from these options. How we can reduce the risk of carbonation induced corrosion to our structures and also promote the sustainability in selecting a material for a particular use. Okay, we'll wait for 1 minute because this is very important. Okay, anyone with the answer? Okay, let's see the answer. So option B is correct. Yeah, some of the people have C or C. Okay, B. Some of ensuring the advocate. Some of the people have seen answer D also. Okay, and let's discuss B and D option then. Ensuring the adequate concrete cover to the reinforcement is possible way of minimizing the carbonation induced corrosion phenomena. That's right, because more the concrete cover, it will take much higher amount of time to reach the carbonation depth to the steel and initiate the corrosion. If we have proper cover, then our corrosion initiation period will be higher, hence the durability of the structure will also be higher. However, some people are saying avoiding the use of supplementary cementitious materials is one of the way we can minimize the carbonation induced corrosion. Yes, that is also true because the use of SCMs reduces the calcium hydroxide content in the concrete that leads to increasing the carbonation rate of the system, and hence if we reduce the use of supplementary cementitious material, we can avoid the carbonation induced corrosion or we can have a higher corrosion initiation time. However, if there is no adequate concrete cover, then if you use or you don't use supplementary cementitious material, the carbonation induced corrosion can happen. So, and use of SCMs is should always be promoted for increasing the reducing the CO2 footprint of cement industry, and by adequately selecting the concrete cover, we can reduce the risk of carbonation induced corrosion. Yeah. Okay. Yeah. Obviously, some because we should not use very high amount of SCMs, like for example 60, 70, 80% of replacement with the SCMs may lead to very higher carbonation, that can lead to carbonation induced corrosion. Yeah, correct. Okay. So next question is on compared to chloride induced corrosion. Carbonation induced corrosions typically occur much faster, especially in humid environment. So occur much faster especially in the humid environment, is more localized and lead to pitting corrosion, affect the larger area of reinforcement, more uniformly, is less dependent on the moisture content of the concrete. So compared to chloride-induced corrosion, carbonation-induced corrosion is typically characterized by which of these factors we will see now. Yeah, please go ahead and you can type your question, you can type your answers in the chat box, or you can unmute yourself for giving the answer. So, and then after this we will see difference between chloride-induced corrosion, carbonation-induced corrosion, how we can characterize them. Let's eliminate some of the some of the options from following. Occur much faster, especially in humid environment. Carbonation-induced corrosion can be the answer. Okay, let's see the option B. Is more localized and leads to pitting corrosion. Will that be correct? Basically not, because we know that the chloride-induced corrosion leads to localized pitting corrosion, and carbonation-induced corrosion is not localized. It is uniform, and it happens on the larger area of reinforcement concrete, and which is typically in a uniform nature. Hence option C is correct. However, some people may say that occur much faster, especially in humid environment, can also be correct. Yes, carbonation-induced corrosion may be faster, typically in humid environment, because now the conductivity of concrete is less. That can lead to an increase in the corrosion rate of the systems. However, in a general sense, because we are comparing two phenomena here, chloride-induced and carbonation-induced corrosion, the option C is more preferably correct. Is less dependent on the moisture content of concrete? Obviously not. Both the chlorides induced or carbonation-induced corrosion is dependent upon the moisture level. If the moisture level is very low, even if there is a chlorides or even if there is a carbonation happen into the structure, still may not corrode at the higher rate. Okay, I think I'm clear. Anyone have any questions, you can ask. Okay, let's see the next question. Which one of the following is common visual symptoms of ASR damage in a concrete structure? Just we now see that what is the ASR, how alkali silica reaction leads to degradation of concrete structures, what is it, why this happens. We also have seen in the previous class. Some of the question highlight on that is like option A is on uniform surface scaling and dusting happens. B, random cracking patterns, often described as a map cracking or pattern cracking happens. Linear crack along the reinforcement. Formation of efflorescence on the concrete surface is the associated with ASR. A little bit very specific question. Think on it and answer. We'll give you 1 minute for this question. Okay, let's see the answer. So people are saying B. Yeah. So option B is correct. Yeah, random cracking patterns, often described as a MAC cracking and pattern cracking, happens because there is a ASR reaction. Why ASR happens? Because some of the aggregates are reactive in nature and they react when there is enough amount of moisture in it, and leads to expansion of aggregate, leads to cracking. So yeah, linear cracking along the reinforcement will happen only when there is a corrosion is happening into the reinforcement. Formation of efflorescence is related to salt attack. Okay, for existing concrete structure showing signs of ASR protein potential mitigation strategies might include. So how we can reduce the ASR? Applying a sealant to prevent further moisture ingress, ejecting the epoxy into the crack to restore structural integrity, reducing the alkali content of a concrete, which is not practically feasible after construction, but yeah, so less the alkalinity, the possibility of ASR is mitigated because now alkalis are less. All of the above with varying degree of effectiveness and feasibility, we can go with this. Yeah. So what is that solution we will do? Okay, people are saying option D we can go for. Let's see the answer. Option D is correct. Yeah. Yeah. Obviously, it is not practical. Yeah, but in the planning stage itself, if we select the cement which has the lower alkalinity content, then the possibility of alkali silica reaction is reduced. Correct. So the next question is on the mechanism of chloride induced corrosion is primarily uniform loss of steel mass over the large area, localized pitting corrosion leading to significant reduction in steel cross section at a specific point, expansion of concrete due to the formation of rust, chemical reaction between the chlorides, ions, and hydrated cements compounds. Expansion of concrete due to formation of rust. Yeah, so only one option is correct. We have seen that there type of corrosion happens, where is chloride induced corrosion and carbonation induced corrosion, and we have seen that carbonation induced corrosion is little bit uniform in nature and affects the larger area. So now this is about a chloride induced corrosion, which, yeah, anyone with the question answer? Okay, so obviously the uniform loss of mass over area is not answer. We have eliminated that point. Chemical reaction between the chloride ions and hydrated cement paste, hydrated cement compounds. How can that lead to corrosion? Okay, so that is also not option. B and C. Let's see the answer. Answer B is correct. Localized pitting corrosion is a characteristics of chloride induced corrosion, and that lead to the very high amount of steel cross section area loss at a specific point that can reduces the load carrying capacity of structures, because now the cross section at a particular point is reduced, which will reduce the tensile strength of the steel, hence, or which will lead to the tensile capacity of the steel because of stress concentration on that point, and that may lead to a catastrophic failure of the structures. Hence, chloride induced corrosion is very critical if we see the different type of durability criteria or the different type of attacks. Chloride attack is very severe. Obviously, expansion of concrete due to the formation of rust will always happen. It's not exactly the expansion of concrete, it's expansion of rust itself that lead to the cracking into the concrete structure. So this is also wrong. Okay, let's see the next question. The rate of chloride ingress into the concrete is influenced by now. We know that the chloride ingress only happens when there is a chloride present at the steel concrete interface, right? And that should be in some amount, and above that, then and then only it will lead to initiation of corrosion by chloride induced corrosion. Okay, that depends upon the steel and concrete properties, and many literature is also available on that aspects. Hence, in our case, we are focusing on how to reduce that ingress of fluorides and reaching the steel concrete interface, which is eventually leads to lowering down of corrosion initiation. So that we can do by the color of the concrete, the type of aggregate used, the permeability of concrete, which is related to the water to cement ratio of and curing, and the ambient air pressure. Obviously, we want to reduce the ingress of chloride ions. We will play with its permeability. We'll reduce the permeability by reducing the water to cement ratio and enhance the curing to form the very dense microstructures. So hence option C is correct. And the type of aggregate may also have some influence, but not much, because the most of the time the chlorides are very small, which passes even from the paste itself. Yeah, so The next question is minimize the risk of chloride-induced corrosion in the reinforced concrete, especially in the environment where chloride might be present. It is important to use a concrete with the high water to cement ratio. Ensure adequate concrete cover to the reinforcement. Use of high permeable concrete to allow chloride to reach out. Avoid the use of corrosion inhibiting admixtures. It's easy, very easy question. Will not take much time. So option obviously ensure the adequate cover to the reinforce is correct because use of corrosion inhibiting admixture is helpful in reducing the corrosion induced by chlorides. So hence we should not avoid it. Use of high permeable concrete, obviously not. More the permeable concrete, more chlorides will come inside. Use of concrete with the high water to cement ratio, obviously not. Higher the water to cement ratio leads to porous concrete, leads to increase in the chloride increase. Okay. Repair strategies for reinforced concrete damage by chloride induced corrosion might involve. What are the different steps involved in the repair of reinforced concrete structures which is affected by chloride induced corrosion? Let's see simple patching the small concrete with the fresh mortar. That is one option. Removing the contaminated concrete, cleaning the reinforcement and applying the corrosion protection before repair. That's the second one. Applying carbonation resistant coating, increasing the traffic load on the structure to compact the concrete. Wow, that is an innovative approach. Let's see what are the answers. Obviously C is the not answer because applying carbonation resistance will lead to reduction in the carbonation, not chlorides. Obviously that option is not correct. Increasing the traffic load onto the structure to compact concrete will not be feasible into the hardened state because the structures have already gained its full strength and further compaction is not possible. Yeah, but it's possible into the fresh state. We can compact the concrete, make it very dense, and that can enhance the permeability properties, will reduce the permeability and may even help in reducing the chloride induced corrosion. Hence, let's see the answer. Answer B is correct. We have to remove the contaminated concrete where there is an ingress of chloride. It's already happened because let's say we are only removing the concrete from the affected area and not from the unaffected area where there is a further time is required to reach the chlorides to the steel. Then in the later stage that chlorides will reach to the steel and then that can leads to even increase the corrosion rate. And also if there is some amount of concrete we have left just behind to the bar which is contaminated, and that contaminated concrete can also even start corroding. Hence we have to undercut the concrete also, and we have to place new concrete which is not having the problem of fluorides in it. Okay, let's see the next question. Which of the following is an active method of corrosion protection for steel reinforcement? There are passive and active protection, which are active using epoxy coated reinforcement, applying this silane based coat to the concrete surface, cathodic protection using sulfate resistant cement. Obviously we want to actively stop the corrosion, actively protect the steel from the corrosion. Hence the cathodic protection is the active method. All other are passive methods using epoxy coated reinforcement. It's like barrier type of coating, so it's passive in nature. Applying the silane base which will reduce the ingress of chlorides in it, using sulfate resistant cement as not relevant in this aspect. Okay, the next question on corrosion inhibited admixtures work by making the concrete more porous, forming a protective film on steel surface, increasing the electrical conductivity of concrete, reacting with carbon dioxide to prevent carbonation. Just now we have seen that the carbonation inhibiting admixtures are used to reduce the corrosion rate into the reinforced concrete structures by protecting the passive film, strengthening the passive film, reducing the cathodic reaction or the anodic reactions, or forming a strong added protective layer. Hence, the option B is more appropriate. Forming a protective film on the steel surface, reducing the aggressiveness of environment is the solution for reducing the corrosion rate. The next question is on when considering the corrosion protection for a new bridge project, let's say in Maharashtra, expected to have a longer service life. Comprehensive approach would like to involve what that is requirement of that structure if you want, let's say service life of more than 100 years, and that is also you want assurity in it. What is that approaches you will adapt? Focusing slowly on achieving high compressive strength of the concrete, you will achieve very high compressive strength. Then you are thinking that your durability of concrete is very high, will be high, and that will give you very long service life. That is one approach. Primarily relying on regular maintenance and repair. Yeah, you are saying that we will regularly maintain and repairs, hence the service life will be higher. C option is the combination of good design practice, adequate cover, quality material, low permeability of concrete, potentially corrosion resistant reinforcement, and possibly active protection method is the critical areas to be considered for longer service life. Choosing the cheapest available construction material to minimize the initial cost, and maybe then that you can put in the regular maintenance and repair is not a good idea. Hence, option C is correct. Designing approach, adequate cover, and low permeability is the factor which will govern the how that system is behaving, and possibly if you have the active protection, whether it's like sacrificial and not cathodic protection or impulse current cathodic protection, that can prevent the further corrosion which is initiated because of chloride induced corrosion or carbon induced corrosion, right? Okay, let's move forward to the next question. Now we will see some of the specialized concrete used in the construction industry. For example, fiber reinforced concrete, self-compacting concrete, lightweight concrete, ultra high performance concrete, and many more. Now this question is on the fiber reinforced concrete. It's characterized by inclusion of short and discrete fibers primarily to improve its. So why we use FRC? What is the reason for using the FRC? So the first option is on the compressive strength increment. Will that lead to increase in compressive strength, or that will increase the workability of the concrete, or that is responsible for increase in tensile strength and the crack resistance of the concrete, or the option D is on the density of the concrete. So I will give you 1 minute to answer the questions, and then we will move forward for the next question. So now we have used the concrete where there is a fibers we have used. So what that fibers is going to influence the properties of concrete. Okay, people are saying the tensile strength of the concrete and the crack resistance will increase. Let's see the answer. So option C is correct. The FRC is characterized by including the short and discrete fibers, and the properties of the fiber is having the high tensile strength. Basically, this is polypropylene fibers or polymer type of fibers, or even steel fibers we use, and what that leads to is that leads to a bridging of a crack. For example, the crack is happening in such a way, then this will bridge this gap by this fiber, and that will prevent the further opening of this crack and leads to increase in tensile strength and the crack resistance of the concrete. Eventually, we are increasing the tensile strength and the flexural capacity of reinforced concrete structure by using the steel fibers. Okay, then second question is on the primary mechanism by which the fiber enhances the property of concrete is by. Just now we have seen that how it's bridging the crack, chemically reacting with the cement matrix to form stronger compounds, physical bridging cracks and transferring stress across them. Just now we discussed, so we will not discuss further. So option B is correct. We have seen that this will bridge the gap and will prevent the further opening of the cracks, that will reduce the formation of cracks, and that cracks is forming a bigger crack by coming together. So that will not happen because of the presence of fibers in it. Okay, so eventually it will increase the tensile strength of the concrete. Okay, so the next question is on, just now we have seen that regarding the properties of fiber reinforced concrete, how it will improve the tensile capacity. Now we will see about the key component that contribute to high strength and durability of UHPC is often the inclusion of. For example, just to clarify what is UHPC, it is ultra high performance concrete where its performance is also high and its or even in ultra level, which having very high, ultra high performance concrete. The performance is very high. For that, what is the requirement? We will see the larger amount of coarser aggregate, very high water content, steel fiber, and highly optimized mix design with this micro silica, and only large and smooth aggregate. So just to clarify that, the UHPC is characterized by having the strength of, let's say, more than M30 MPa, right? M30, sorry, 130 MPa. Typical concrete is having the compressive strength of around 30 MPa, 40 MPa, 50 MPa. Nowadays we are basically going with the 50 to 60 MPa for general construction, like reinforced concrete in the normal residential buildings and bridges. But very specialized concrete is used for very special purpose, which is having very high strength, called as USPC. So how we can achieve that strength? What is the constituent we have to use to achieve that strength? Shall we use larger aggregate? Shall we use very high water to contain? Very high water content? Shall we use only smooth aggregate, or what? Can answer your in the chat box. Okay, people are saying C answer. Let's see the answer. Answer C is correct. Yeah, obviously we want a very high strength, so even the tensile capacity we want better, like very high compared to the normal concrete. The steel fiber will help in that to improve its even compressive strength and reduce cracking. Highly optimized mix is that will use very fine aggregates and very high content of binder. For example, microsilica we will use because that is very highly reactive and will form a very dense microstructure and leads to increase in its strength. Okay, the next question is on the typical water to cement ratio used in USPC is greater than 0.5, around 0.4, less than 0.25, less than 0.35. It's very easy question. I will not explain much about it. So which is that range we will go for UHPC? So hence, and also how to achieve that also I would like to hear from you guys. Anyone with the answer? Okay, let's see. So achieving the ultra high performance strength and the performance of the concrete, we require a very less water to cement ratio, which is even less than 0.25, and achieving that and achieving the workability required for placing the concrete is also important. Then hence the use of supplement super plasticized is very essential in this condition, and we have to use SP in a very high amount to provide the fluidity to the mix. Lesser the water to cement ratio will give higher the strength and denser the microstructure. Okay, so the next question is on UHPC. As due to the high strength and the low permeability of UHPC is being increasingly considered in infrastructure projects, like example in a Bandra we're listing in Maharashtra, including the potential in the Maharashtra for application much as. So now you know that it's because of its high strength and high performance, which of these areas we will use the UHPC. So the option A is that temporary scaffolding, non-loading bearing walls, bridges and girders with a longer span, and thin overlays of deck rehabilitation, standard residential flooring. So just now I think partially I have answered this question also, so we will not okay, option D for the previous. Yeah, option C is correct. Option 0.35 is also possible to achieve strength, but moreover it will not reach of UHPC level, hence option C is more appropriate. Focus on this question now. The next question is on where we will use UHPC. Basically UHPC is very high rich cement content mix, and because of that it's a little bit expensive because of uses of fibers, also steel fibers, specialized steel fibers. Hence it is only used where there is a very high requirement of longer span and the high requirement of strength is requirement, and we have to reduce the weight of elements, for example, the longer span of bridges, and hence we have used in Maharashtra for the Bandra Worli ceiling. We have in Mumbai, where the longer span is the deck of that is the I section of that is constructed using the UHPC. Okay, option C is coming as correct. Yeah. So again, in FRC, fibers are typically fiber reinforced concrete in which continuously embedded throughout the structure elements like traditional revas is typically uh, presence in FRP, or short, discrete and random distributed within the concrete matrix is the property of FRC, or align in a specific direction to resist the primary tensile stresses, or used only on the surface of concrete members for aesthetic purposes. So why we use FRC, fiber reinforced concrete, and how it is distributed is the question. Please answer. Sorry. Yeah. So yeah, please. I will be on this screen. Yeah. It will be very easy if you unmute yourself, and then, or I will wait for 1 minute to check the answer. I can't switch screen for today. Okay, let's see the answer. We'll eliminate it. Continuous embedded throughout the structure element is for the reinforced concrete structure, not for FRC. So hence, align in specific direction, and this is primary tensile stress is also not correct. Aligning the fibers is very difficult. We will not do must not do will not prefer that, and this aesthetic is also not correct. Hence, B option is correct. Short, very short, discrete, and randomly distributed within the concrete matrix to prevent the cracking or bridge the cracking. Okay, compared to plain concrete, FRC generally exhibits. Now, what is the advantages of using FRC? Lower ductility and toughness, higher resistance to shrinkage crack and improve impact resistance, reduce fire resistance, increase permeability. Just now we have seen that the fibers leads to cracking of, bridging of cracks. Hence, what could be the answer? Obviously, the answer is lie on higher resistance to shrinkage cracking and improve impact resistance, right? Sorry. Yeah, hence B's answer is correct. Reducing the fire resistance is not always true. Increase in permeability, obviously not. Lower ductility and high toughness, obviously not, because the incorporation of FRC leads to increase in ductility and even increase in the toughness of concrete, which is also helping in improving the impact resistance of concrete. And that's why generally nowadays in a PQC type of construction, in the roads, the rigid pavement, we use fibers to increase its toughness. Okay, one of the following is the primary characteristics of self-compacting concrete. Now we see SCC is having the high compressive strength, ability to flow, consolidate under its own weight without vibration, low water to cement ratio, use of lightweight aggregate. This is very easy question, so we will fast forward it. Obviously, the ability of flow and consolidate under its own weight is without vibration is called as SCC concrete. What is the purpose of using it? Because in the area of very high congested reinforcement, very high density of reinforcement, it's very difficult to compact the concrete, and if you use the normal concrete, it can lead to the formation of honeycombing. Hence, we want a concrete which is self-compacting by its own weight in that areas. It is very useful to use a self-compacting concrete. Okay, which one of the following is common method to produce lightweight concrete, and what are its advantages? We will see now. Use of very high water to cement ratio, incorporating the lightweight aggregate, adding the large amount of fly ash, using the only fine aggregate. Okay, option B, yeah, it's correct. Incorporating the lightweight aggregate is the correct answer, because we want to reduce the weight of the concrete, then obviously what is that element in the concrete which is occupied bulk and its volume is the aggregate we use. If we use the lightweight aggregate, we will get lightweight concrete. And if we use the high weight aggregate, like for example lead and magnetite and where it's a iron when it's very high in that aggregate, we can also produce the high weight, lightweight, or maybe heavy weight concrete. Usually typically that is used in the nuclear shielding into the nuclear power plant, where we will use very high weight aggregates, like the aggregates made up from lead, or even made up from the steel, like cutted steel in the an aggregate form. Okay, hence that's for today's class. We have covered the content on different specialized concrete, like lightweight aggregate, and then we have seen self compacting concrete also. We have also touched upon FRC, fiber reinforced concrete. We have seen how it bridges the crack between the crack forming in it, and what is the typical nature of distribution of fibers we have seen. And we also seen some question about UHPC, where it is used and what is its purpose, what is its water to cement ratio typically used in that conditions, what is its compressive strength in UHPC. We have also seen some mechanisms related to the fibers and properties, increasing the properties of concrete by using fibers in a general. Then we have seen some of the properties related to how to achieve the higher service life in a concrete structure, what are the properties we should consider, for example good design practices, quality of material, low permeability of concrete, and even possibility of active protection method for corrosion resistance we can use to enhance the service life of concrete structures. Corrosion inhibitor and its effectiveness, and how we can use, and cathodic protection also we have seen. And then also we have touched upon some of the properties of repair strategies and reinforcement and damage chloride induced corrosions, how to mitigate that, use of lower water to cement ratio, lower of permeability will reduce the ingress of chlorides, can reduce the possibility of formation of chloride induced corrosion we have seen. Then chloride ingress, how to reduce that also we have seen, the mechanism of chloride induced corrosion, and also ASR also we have covered, the alkali silica reaction, how it can form the pattern cracks, how we can reduce it, how like use of lower alkali cement, use of non-reactive aggregate can help to reduce the that. Okay, then also we have seen some of the general form of corrosion, chloride induced corrosion, carbonation induced corrosion, how we can prevent it, how to reduce the carbonation induced corrosion, what is the carbonation, what it leads to, reduction in the pH, how the carbonation rate influences with the RH also we have seen. And then some of the properties of carbonation and what it reacts, which constituent of the concrete reacts first with the CO2 that we have seen. Some of the related to sulfate attack when it happens, the following like sulfate, like how to increase the sulfate resistance of the concrete also we have seen. And which are the sources of sulfate attack, like for groundwater and some of the soils which contain sulfates we have seen in the short. So concrete and durability aspects this is not week 10, this is week 11, and we are in the second last live session of the modern construction material. If you have any questions, you can contact me on mail ID or a discussion forum. We are very active there. You can contact me here, or maybe in discussion forum. So this for the today's live session. If you have any question, please mail me here. Thank you all for joining, and we will close today's live session. Okay, thank you all for joining. We will see next live session, same place, same time, next week. If you have any question, please mail me, and this video will be available online within 2-3 days. Then you can rewatch if you have missed some of the questions during the live session. Thank you all.